Welcome viewers, welcome to this session of teleconferencing. You are going to be told today, or rather we are going to discuss today about the course MEC 003. This is the course on quantitative methods in economics. Now, from this course we'll be taking a single topic, that is on integral calculus and economic dynamics. Integral calculus is part of a quantitative techniques which follows from your earlier teleconferencing session which you had some days back, which was on linear algebra, and this session will deal with the concept of economic dynamics and will ask you to understand what dynamics mean in the context of economic processes, how it differs from statics, and where the role of integral calculus and other related techniques come in. To begin with, let us discuss the concept of statics and dynamics. Now, if you were to look at the first slide that will be shown on your screen right now, could we have the first slide, please? Yeah, it's a slightly small. I hope you are able to read what is there on the smaller fonts. But basically it says that there are three kinds of techniques, that is statics, comparative statics, and dynamics. You'll see that statics deals with equilibrium at a point of time, comparative statics shows change in equilibrium due to change in parameter values, and dynamics deals with change over time, which is what we'll be discussing in this session today. And it further says that the basic tools for dynamic analysis are integral calculus, differential equations, and difference equations. Okay, now let us take up the discussion of these topics one by one. Now let us see what statics mean. Statics basically means equilibrium at a point of time. You have all known the theory of demand and supply, and you know the concept of equilibrium. From your microeconomics course, for instance, you know the concept of equilibrium, and you know that when demand and supply curves cross, or if you have an equation for a supply function and an equation for a demand function, then you will know that they interact and intersect at a certain point, and that is the equilibrium point. Now that point, that equilibrium point, is an equilibrium which is static in nature. It is at a point of time. Now, what does comparative statics mean? Comparative statics basically means that, say, let's again talk of demand and supply. You know that the demand for a commodity depends not only on the price of the own commodity, the same commodity, but also on the income of the consumer. So, supposing we say that the income of the consumer goes up, now what happens to the equilibrium? In that case, you know what will happen is, if the income of the consumer goes up, then the whole demand curve shifts to the right. Now when the whole demand curve shifts to the right, you will arrive at a new equilibrium point, which will probably be above and to the right of the old equilibrium point. We will not go into this thing. It's just by way of illustration that this is a static equilibrium, because you had a static equilibrium, you change some parameter values. In the case of demand function, the parameter is an income of the consumer. So due to the change in parameters, you come to a new equilibrium point. Now if you look at the next slide, you'll see, can we have the next slide please? So this is Now we come straight to integral. Why have we come to integral? Because we say that we will be dealing with a long-term process which deals with dynamics. A dynamics, we'll see how dynamics relates to the concept of integration, and that says that dynamics means that something that takes place over a period of time. Compared to statics, and statics deal with equilibrium at a point of time. Here we are talking of equilibrium over a period of time. But before that, let us just look at the concept of integral and just see what it looks like. If you look at the screen, you will find some mathematical symbols. Now let us begin from the extreme left. That elongated S is actually the integral sign, and it says that if you have a function x, that is, you have a variable x and a functions of x, say call it y, but just for simplicity we will be writing fx here. Now fx dx, now fx dx are together, they are not products. Fx dx, the integral of fx dx is a capital fx. It's a new function. Now this capital F is also a function of x, and this is an integral. You can think of integral as a summation. You have fx ds, think of it as summing over a large number of such things when x tends to 0. So it is infinitesimal changes in x. Dx stands for changes in x which tend to 0. Now you can, when you think of x, just put, instead of x, put t. Let t stand for time, just as a conceptual measure. Let t stand for time, and then you will find that something that is a function of time. What can be a function of time? Let's say national income, gross national product. It changes over a period of time. It changes over time. So what we are saying is that as time changes, it need not even be time, it may be quantity. Let's say x is output, and fx is a function of the output, say cost. As output increases, cost increases. If fx is, small fx is average cost, then an integral of average cost is total cost. We'll come to all this later, but just for the moment, just focus on the things that is there on your slide. The next, continuing the capital fx, you'll find that it is just the opposite of differentiation. If you integrate small fx, here small fx is known as the integrand. If you integrate small fx, you get a capital fx, which is, if you arrive at a converse way, if you differentiate capital fx, you arrive at fx. Therefore fx, integration and differentiation are inverse topics. Now the next line says that fx and dx, d of fx is the same as the differentiation of fx plus some constant c, because you know the differentiation of a derivative of a constant is 0. So whether a derivative is there, that constant is there or not, you will still get small fx, right? Because if you, even if you differentiate capital fx with dx and there is a constant c, you will still end up getting small fx. So what we are doing in fact is that you are getting a derivative of fx regardless of whether you have a constant along with it, and you get the same answer. Therefore, looking at it in a converse manner, if you integrate small fx, there's no harm in putting a constant of integration which we call c. Just for conceptual clarity, we say that integration of a function fx is another function which we have denoted here by capital F or c. And therefore, if you come back to that, we'll come back to that slide. Yeah, we were on this slide, and therefore you'll see that fx, small fx integration the same as an answer with a constant of integration. Because of this reason, indefinite integral, we are calling it indefinite integral because x here has no interval bounds. We'll come to what is a definite integral subsequently, but for the moment we are just dealing with an indefinite integral, and it is just a converse of differentiation. Therefore it is often known as antiderivative. Now let's take a look at the next slide. We carry on the discussion from here, and let's take a look at the next slide, and it just gives you some formula. This is for the computation. so it says that if you have integral of x raised to the power n, then you just add a 1 to that power and divide that thing by the power. For instance, if you have x square, an integral of x square would be x cubed by 3, plus of course the constant of integration is there. Similarly, integral of 1 by x dx is a natural log of x, and so on and so forth. These are for your computation. This is there in your unit also, and if you practice some problems which are there in your unit, which I'm sure you have done, then you are really been able to get the computational formula. Now, integral calculus is a method of, as we said, coming to a situation which is the converse of differentiation. Now, carrying on from here, just go on to the next slide, and it just carries on with some rule which says that an integral, let's begin with the second one, which is simpler, which says that integral of the negative of a function, right, is the minus of the answer of the integral, which means it sometimes aids in computation. If you have a function, then it often aids you. If you have a negative of a function, it helps you to know that the answer would just be the negative of the function, negative of the answer of the integration. Suppose you integrate a function and the answer that you would have got, and instead of integrating that function, if you integrate the minus of that function, the negative of that function, then the answer of that integration would be the negative of the answer of the previous integration. Similarly, integration of a function which is multiplied by a constant is the constant times the integration of that function, which is the first rule which is mentioned here. And the third one actually combines the first one with a rule of, which we have not mentioned separately, which says the integration of a function fx plus integration of a function fx plus a function gx, the integration of the sum of these two functions is the sum of the integral of these two functions separately, which means an integral of fx plus gx is the sum of integral of fx plus the integral of gx. Now, with this, you combine the first rule, which is right at the top, then you get the one at the bottom, which says if you have a function fx and you multiply it by k1, which is a constant, and if you have another function gx and you multiply that with k2, which is a second constant, and you add up these and you take the integration of this final value, then this will be the same as k1 into the integral of function fx plus k2 into the integral of gx. Finally, we'll come to the next slide and then we'll carry on with some conceptual discussion. If you look at the next slide, it just tells you a method of substitution which says that if sometimes it helps, I mean sometimes integration is you have to adopt some tricks. I mean differentiation in a way is simpler. If you have done computation of differentiation, you get directly there are some rules and you apply that. Integration, along and apart from the rules that we just discussed previously, I'll just be discussing two more very widely used method. One is the method of substitution, which says that sometimes it helps you to write x as a function of another variable y. Supposing if you have x and you can express it as a function g of y, then it stands that fx becomes, right, x becomes gy, that much is clear. But then if x is gy, then in that integration the dx will become g dash y, g prime y dy, where g prime y stands for the differentiation of g. So instead of finding the integration of fx dx, what you do is you find the integration of, you have expressed x as gy, then you take the derivative of g and you write that g prime y dy. So this gives you sometimes an easier method of obtaining a solution to a set of integration problems. Second method that we discuss is what is called integration by parts. Now this has been written in a very concise manner. What it basically says is, the top line says that you know from your differentiation rules that if you have two variables u and v, which are both say functions of x, then d by dx, it does it's incomplete, it doesn't say d by dx. On the left hand side also, on the top equation, it should be d by dx of uv is u into dv by dx plus v. Again there is a typographical error. The second one should not be equal to sign, it should be a plus sign. It's an oversight. Kindly note that it is u dv by dx plus v du by dx. Right? This is from your differential calculus. Now you use that, and if we were to integrate, then using this you will get an integration of uv prime, where uv prime, that prime stands for differentiation. Integration of uv prime dx will be the same as integration of u into v prime dx plus integration of v into u prime dx. This just follows from the top rule. Then we rearrange the terms. Then we say that u into the v dash dx, there is an integration sign there which is again missing, is equal to uv minus v integration of u dash ds. It looks a little tedious while you just and try, I'm sure, when you are looking at it right this, but the trick to understand this is to really look at some problems, a lot of which are there in your unit and in your check your progress exercises, which I'm sure you have attempted by now, and there are a few problems on this in your assignments, and therefore if you do these problems, and the idea, you have to use a judgment when you solve integration problems as to which one would require integration by substitution and which one would require integration by parts. Now from here we can probably carry on the discussion and look at some of the applications. Alright, now the first application, and let us discuss this a little in detail, and says that let us look at the investment problem. Now what is investment? An investment is addition to the stock of capital, right? Now which means as time changes, capital increases if there is capital accumulation, and that is the economic definition of investment. We are not here talking of a financial investment in the sense that you invest in a financial asset and you get returns. Let's just for simplicity talk of addition to physical stock of capital in the economy. As time changes, say time changes from T1 to T2, then the stock of capital increases, say from K1 to K2. Now what has happened is the increase in capital is K2 minus K1. Let us just say, let us call it delta K. You know delta is often used symbol for change. Then delta K by the change in time, which is T2 minus T1, and that would be the change in time. Then delta K by delta T, as delta T tends to 0, which is infinitesimal changes, that shows you investment, right? Now what happens is that investment is nothing but the addition to the stock of capital, and we expressed it through the root of differential calculus. Now at the beginning of the discussion itself, you were told that integration, that indefinite integral is known as antiderivative, which means that it is the inverse or the converse of differentiation. So which means if you were to go back and look at the slide that comes up on your screen in a little while, can we have the slide please? If you look at the slide, you will see that it will show you that investment, it says the first equation says IT is equal to, T stands for time, and when you're dealing with continuous variables rather than discrete, here time is not broken up into segments, yet time is talked of in as continuous time without any break, then you show T within bracket. So it says that investment at a point of time is the change in capital over the change in time, which means if you turn it around, the capital stock at a particular time is nothing but the integration of investment, right? Which means what? Which means that if you look at the equation carefully, the second equation carefully, you will find it sounds slightly paradoxical. We have said that investment is the addition to capital, right? Sum total of capital. And we said at the beginning that integration can be looked at as a sum, as a sum which is as the changes tends to 0. But here the second equation makes it seem that integration is summed, and rather investment is summed and you get capital. It sounds very paradoxical. Do we sum investment and then do we add up investment and then come to capital, or do we add up capital? We are adding, accumulating capital. Why does it look like that? Well, the answer is that at any given point of time, capital is increasing, and this change in capital is just the name for investment. So what you're saying is that kt, dk by dt in the top equation, if you were to just take t to the other side, you will get it dt is equal to dkt, right? Now all you have to do is to integrate both sides. Integration and differentiation cancel each other out. So on the right hand side you have integral and then dkt, so the integral and the d cancel each other out. You are left with kt, which is shown as the left hand side on the second equation, and the left hand side of the first equation now becomes the right hand side of the second equation, which you get integral of it dt. So this is this is a way of, if you stare at the equation for some time, you will get an idea, you get a grasp of the hang of what exactly investment and capital are, how investment and capital are related to each other, and that helps you in understanding the relationship between differentiation and integration. Just look at the equation, it's there in your equation unit also for some time. Now let us look at another application. In the next slide you'll see that it says that one thing that we can do about integration is to get the total from the marginal. Now in your microeconomics, what we have done usually is marginal analysis, right? You have been told that, well, there's a total say total revenue curve and there's a marginal revenue curve. You have been given the total cost curve, and from the total cost curve you have obtained the marginal cost curve and the average cost curve. By to obtain average cost curve, you have divided the total cost by the quantity, and to obtain the, say, the average cost, you have divided you have differentiated the total cost with respect to quantity. And indeed, when you were looking at profit maximization or cost minimization or maximization of utility, the first order conditions were telling you, say first order conditions for profit maximization was telling you that marginal revenue ought to be equal to marginal cost, right? Now what does it mean? It means that you are usually dealing with marginal quantities. In fact, much of neoclassical economics, which is what your microeconomics is, your course MEC 001 for instance, you will find the conditions for optimization often state that marginal revenue is equal to marginal cost or marginal utility is equal to price. So you are dealing with marginal quantities. Therefore, in fact, it is sometimes known as marginal analysis. The whole exercise, the whole way of dealing with these problems is known as marginal analysis, because you are dealing with marginal quantities or quantities at the margin. Now, supposing we do an opposite exercise. We are given the marginal quantities and we want to obtain the total quantity. Say we are given total marginal revenue and we want to obtain total revenue. Here our definition of integration comes to our help. We know, number one, that we had obtained marginal revenue by differentiating total revenue with respect to cost, which is what your first equation says, right? And we also know from our discussion of indefinite integration that integration is the opposite of differentiation. So if we can obtain marginal revenue from total revenue via the channel of differentiation, then we can get back from total revenue to marginal revenue via the channel of integration, and that is indeed what has been done in the second equation. You will see that total revenue is nothing but the integration of marginal revenue with respect to quantities. So a very important way of looking at integration is to look at the sum total of marginal revenue into the changes in price. Supposing you had a diagram, you know what a marginal revenue curve looks like. On the horizontal axis, supposing you have quantity, on the vertical axis you have marginal revenue. Then you look at changes in horizontal on the horizontal axis on changes in quantity, and you look at changes in marginal revenue on the vertical on the y curve. Then they form rectangular strips. You sum up those rectangular strips, and we have said that integration is nothing but like a summation taken with very small, infinitesimally small changes. That is the integration, and that is indeed what we have done. Now let us get back to our discussion away from the slides, and let us just carry on a general discussion, and then we'll see what we have studied till now. We said from the beginning that we are dealing with dynamics, which was true, that dynamics means changes over time, and it is also true that integration comes to the aid of our study of dynamics by being the basic tool of dynamics. But it is equally true that integration, if we look at dynamics, if you, let's say we want to study changes over a period of time, then what technique do we use? Well, we use integration. But if we have integration as a tool, then where all can we apply it? Well, dynamics is an important area where we can apply it, but dynamics is not the only area, because we have just seen in that last example where total revenue was obtained from marginal revenue by integrating the marginal revenue function, that integration is of use in two ways. One, as dynamic analysis, as changes over time, which was our first example, which was the relationship between capital accumulation and investment, or capital in investment, where indeed accumulation of capital over time means it is a dynamic analysis which we are talking about, and therefore we are getting investment, which is a pure dynamic analysis, and we are using integration. But the second example shows that integration can be used for areas other than dynamics, where to obtain total from the marginal. And we gave the example of total revenue being obtained from marginal revenue. You can as well use it to obtain total cost from marginal cost and other total and marginal quantities, total quantities from other marginal quantities. So what exactly have you understood? A, that integration is the opposite of differentiation. B, integration is like summing, and summing over a certain change in a quantity. As a quantity x changes, the function of x is summed over the period of that quantity. That is the second thing we have learned. Third thing, which is very important for you to remember, is that the indefinite integral is actually also a function of x. What does it mean? It means that we have shown a function small f x, which we had, if you remember the slides that we had shown, a small fx, when you integrate it you get capital fx. But the thing to remember is that small fx is a function of x, the capital fx is also a function of x. It's a different function, but it's also a function of x. Now let us look at another kind of integration, which is known as the definite integral, which is slightly different from indefinite integral, and that is what we will discuss now. If you look at the next slide that will appear on your screen, you will find that we are talking of a definite integral. Now can we have the next slide please, so we can see the discussion from there. Definite integral of the function is integration of x over a given specified interval, which means think of a horizontal axis x, that x is going from 0, even if we take positive axis, 0 to indefinite to the right. Now we don't want that, we just want the change in x from a starting point a to a starting point b. A and b both are of course included, it's not an open interval, therefore we have these square brackets. In an interval a to b, within this interval fx has changes, x has gone from fa and then has gone to fb, but what is the total change? The total change is that it is expressed as, we write fx dx as in the improper integral, but if you see the sign of integral, the top and the bottom have b and a, they show the endpoints of the integral, that is the interval of the integral. It says you integrate fx over the integral a to b. Now the thing to remember, the basic difference between definite integral and indefinite integral is, we have said the indefinite integral is also a function of x, right? We said a little while ago that supposing you had that fx, in the case of indefinite integral, the answer which we denoted by capital Fx is also a function of x. So you integrate a function of x, you get another function of x. But here, in the case of definite integral, the answer that you get is not a function of x, but it is actually a single number. Now if you look at the next slide, you will see that it is shown as the limiting sum of, it is slightly inverted, but it shows the limited sign of sum of fx. It's not come out very clear, so let me just tell you what it actually stands for. That is just you see the summation sign. The next is actually the mirror image of f. Instead of fx, it has been shown as the mirror image of x and fx delta x. So what happens is that, see, what happens with the case of definite integral is that x changes within the interval, x changes from a to b. That change in x we have denoted by delta x, right? Now the horizontal part is delta x, the vertical part would be fx. Now vertical into horizontal will be a one rectangular strip, right? The trick to get a diagrammatic idea of definite integral, which you are not showing here, is that you divide the interval between a to b into very small, many small strips, many small pieces. Like say supposing you go from a to x1, then from x1 to x2, x2 to x3, so on till xn to b, right? This distance from a to b you divide into many strips, and the vertical axis would be fx as the value of fx at different point. So change in x into vertical axis will be the area of one rectangle strip. You sum up all this area of the rectangle strip, you will get a definite integral. So a definite integral, conceptually definite integral can also be understood as the area under that diagram, the curve fx from the horizontal axis, the area between the horizontal axis and the curve fx, that entire area is known as a definite integral. Now from here, if you look at the next slide, you will see that there is a fundamental theorem of calculus. This is something that you must remember. It is called the fundamental theorem of calculus, and it says that if the integral of fx dx from small a to small b, which is the interval, is equal to, actually it should not be small fx, it should be capital Fx. If the integral of fx dx, small fx, can be denoted as capital Fx, then the integral of fx dx is the same as substituting the value of capital F at the point b minus the value of f at the point A, right? Which means that to compute the integral, you can even do it diagrammatically. What you have to do is you integrate the function fx. You are given fx, right? Integrate that function fx using any technique of substitution or parts or all the formula that we had given in the case of indefinite integral. You've got that, right? Now, whichever the function of the answer that capital Fx you have got, you have to substitute two values for it. First, you have to substitute the value b. Okay. From here, you calculate, then you substitute the value a. A and b are given to you. On that left hand side, supposing that b is 10 and the bottom a is 5, then you have calculated fx, capital Fx, you have got the type of function. In that function for x, first you substitute 10, which is b, you get an answer. Then you substitute a, which is again an answer. Then you subtract capital Fa. There is a mistake in this slide, for which I am sorry. It actually, on the right hand side, please remember it is capital Fx. It is just like the answer that we had given in the case of indefinite integral, right? So you have capital Fb minus capital Fa. So this again brings us to the point which we had said at the beginning, that indefinite integral is a function. There's not, you have a given function, say x cube. Let's say you have x square, right? X square is a function of x. You don't know what is x square. You don't know the values of x. Therefore, you cannot find the values of x square. You have x square. If you integrate x square indefinitely, right, then you get x cube by 3. That according to the formula that we had given. Now again, x cube by 3 is again a function of x. You don't know that it is not a number. That value will depend on if you whatever the value of x you put. Till then, it is just a function. So from a function x square, you integrate, you get an x cube by 3. Instead of that, supposing I have a function x square and I integrate between, say, a is equal to 2 and b is equal to 3. Then first I integrate, I've got x cube by 3, again in the case of definite integral. Now instead of x, first I put x as 3 because the top b is 3 in our case. Now 3 square, what is 3 square? 9. 9 divided by 3, what is 3 square? 9 divided by 3? 3. So FB you have got as 3. Now you come to FA. What is A? A was 2. Now you have, I'm sorry, FB would not be 9 because it is x cube. So it is 3 cube, that is 27. 27 by 3, which is 9. FB is 9, right? Now FA, A is 2. 2 cube, which is 8 by 3. 8 by 3, which is something like 2 point something. So from 9, you subtract 2 point something, you'll probably get 6 point some, close to 7. So here in the case of definite integral, as you can see from the computation which I have just spoken out, using the formula which is there on your screen and the slide, in the case of definite integral, what you are getting is an absolute pure number. It is not a function because the endpoints are given to you and therefore you can obtain a number. Second point to remember is, in the case of definite integral, in the case of indefinite integral, you put a c, a constant of integration, because conceptually differentiating capital Fx with respect to x, whether or not c is present, you will get small fx. But in the case of definite integral, you need not put that constant of integration c. Now look at the next slide. We'll come, using this slide, we'll come to now some of the applications of definite integral. We will not go into these in detail, but we'll keep this in the concept of definite integral in mind for you to discuss. Let's begin with the first one. It says consumer surplus. What does consumer surplus mean and how can we get it? You know the demand curve. Now let us carry on a general discussion and we need not look at the slide. We'll come back to the slide in a little later, but first let us have a general discussion on consumer surplus. Now you have seen, when you have a demand curve, say at a quantity X on the horizontal axis, the price is P, right? So from a horizontal axis, draw a vertical line till the demand curve, and from that point you draw a horizontal line till the Y axis. Okay. Having done that, you get the total amount that the consumer has paid. But there is an area from above that horizontal line, and a triangular area is formed between the demand curve and that horizontal line. That shows a consumer surplus, and that is defined as the difference between what the consumer paid and what he would have paid or she would have paid if there was a choice of all or nothing. Either you take this or you don't take it. What it means is that consumer surplus in a demand curve, the more you buy, the price is low. It is actually the opposite. As the price falls, you buy more for it. But supposing you have paid, say, 12 rupees for a bottle of water. If the price of the water fell to say 8 rupees, you will probably consume more water, especially in summers. Although there is a certain amount of water you can take, but you will probably consume more water. So what happens is demand function will show that. Now you have paid 12 rupees for the first bottle of water. Supposing you have said that in a situation either you will have no water, or you'll have to pay what is the maximum you are willing to pay for it. Then maybe you would have been willing to pay 20 rupees for water in a situation when the alternative would have been to be without water, but you've actually paid 12. So this difference between 20 and 12 is the consumer surplus. Now the way that definite integral comes into to our aid is that we have said that definite integral also has a diagrammatic interpretation, which we had discussed earlier, that in a horizontal axis interval a to b, you get the area under the, from the curve fx till the horizontal axis. Now think of it as a demand curve. From the demand curve there is a downward sloping demand curve, and on the horizontal axis take two intervals a and b. Say B can be higher change in price P2, and A can be lower price P1. So as the price changes from P to P1, what is the change in consumer surplus? You can use the technique of integral calculus, definite integral calculus, to get it. Similarly, let us quickly go over the other two applications. We had talked of capital accumulation in the case of indefinite integral. The second application here says that capital accumulation, but instead of an indefinite period, we can actually specify the period, which sometimes is very useful for our planning exercises. In Indian planning, supposing you have a 5-year plan beginning 2007 till 2012, let us say, then the lower interval can be 2007, the upper interval can be at 2012. See how much capital is accumulated, and you can use definite integral to mark off the limits and compute capital accumulation. Similarly, present value or discounted value under continuous compounding of interest, as you know that if the interest is compounded continuously, it becomes a limit sum of Ex from the present value formula, and as you change over time Ex, you can set limits and you can get the endpoints. So these are the some of the simple applications of definite integration that is given also in your unit. So today, thank you for listening to us, and we have discussed the indefinite integral and the definite integral, and we saw how these can be useful in the dynamic analysis, and also other than dynamic analysis, they have some applications going from marginal to total, total to marginal. Remember these, but also remember the difference between the definite and indefinite integral conceptually. Definite integral is a single number. Indefinite integral is also a function. Secondly, remember that the indefinite integral can be understood as the opposite of differentiation. The definite integral has no such interpretation. And finally, please remember the fundamental rule of calculus which says that the definite integral between the point B and A is the same as capital FB minus capital FA. And also keep in mind the applications that we touched upon. Thank you so very much for watching this, and if you have any suggestions or queries, you are free to write to us at the Economics Faculty in IGNOU at Maidangadi. Thank you for watching this session. Thank you.